Welcome to Chem-1A at Shasta College. This screencast is an introduction to chemical reactions and reaction equations. And let's start with a demonstration that you might see in person in class. If we take a balloon that has hydrogen in it and put a spark or a match near it, we get a very vigorous, violent explosion reaction type of thing. Lots of heat is given off, and very clearly a chemical change has occurred. Now, what has happened is that hydrogen gas has reacted with oxygen gas from the atmosphere, and it forms water. It's kind of fun. Now, you can't necessarily see the water being formed, but if we did the following, we could demonstrate that it is water that's the product. If we take a robust container, maybe steel container, put a hydrogen-filled balloon in it, make sure there's oxygen around, and then spark it, we get a reaction. Lots of heat's given off. We can't see the products initially, but if we let everything cool down, we start seeing little droplets of clear colorless liquid form on the inside of the container, and we can analyze those droplets and show that they are in fact water. So the reaction that takes place is one that happened on a large scale very disastrously in the late 1930s. You might have heard of the Hindenburg, an airship filled with hydrogen gas that provided it with lift, and it caught fire. And many people lost their lives, and that pretty much ended the use of hydrogen as the less dense than air gas used to fill this type of airship. Okay, well, let's get on to the chemistry of this. We can symbolically write what took place using symbols for the substances. Hydrogen is H2. It's two hydrogen atoms bonded together. It's a diatomic molecule. Same with oxygen. It's two oxygen atoms bonded together, and we symbolize that by O2. And when these combine, so we write H2 plus O2, and then an arrow indicating that they form water, H2O. And this is the start of the chemical equation that describes the reaction that takes place. And we can also look at this in terms of little models of the molecules. There's a hydrogen molecule, two H atoms bonded together. Here's an oxygen molecule, two oxygen atoms bonded together. And a water molecule, H2O, is produced, an oxygen bonded to two hydrogen atoms. Now we note something immediately. We can't have matter created or destroyed during a chemical reaction, and it appears we've started with two oxygen atoms and we only have one to end up with. Well, that can't be. What must happen is we must have a second oxygen atom that appears in the product as part of a second water molecule. Now this means we have two oxygen atoms at the end and two oxygen atoms to start. But we now note we appear to have four hydrogen atoms at the end with only two at the start. Well, that can't be either. We must have four hydrogen atoms at the start. In other words, we must have two hydrogen molecules to start. Now we have a reaction that correctly represents what takes place in terms of not having material disappear into thin air or be created out of thin air. And we show this in the chemical equation as a now about to be balanced chemical equation. We produce two water molecules and we start with two hydrogen molecules. We now have a correctly balanced chemical equation. Now in general, balanced chemical equations are going to symbolize two things: the qualitative changes, in other words, what substances did we start with and what substances were produced, and then also the quantitative changes, in other words, how much of each substance is going to be produced or how much of each substance reacts when we have a chemical reaction. Couple things to note about chemical reaction equations. We use chemical formulas to symbolize the reacting substances, the compounds that react, and those we call reactants, and then the compounds that are produced, which we call the products. So in this particular case, hydrogen and oxygen written on the left side of the reaction equation are the reactants, and water, H2O, is written on the right side, and it's a product. We have what are called stoichiometric coefficients that tell us the relative numbers of molecules, or on a larger scale, of moles of those substances that take place in the reaction. Those are going to be the 2 and the 1, the coefficients out in front. And then we also have state symbols that indicate the phases of each substance that's involved. So here the stoichiometric coefficients are 2, 1, and 2 respectively. And then parentheses G means that hydrogen and oxygen, and as it's produced, water, are all gases. And then, of course, if we let it cool down, water would eventually turn into a liquid, which we would symbolize by L. Let's do a couple examples. A fairly straightforward starting one is nitrogen gas reacts with hydrogen gas to make ammonia gas. And you should be able to not only balance chemical equations, but write a chemical equation from a description of what happens. So nitrogen gas is N2, hydrogen gas is H2, and ammonia is NH3. And make sure you don't confuse that with ammonium ion, which is NH4+. So N2 plus H2 makes NH3, is the sort of framework for this reaction. And then to balance this, we note, and we'll do this one in some detail, on the left we have the reactants, apparently 2 nitrogens and 2 hydrogens. And on the right we have the products, 1 nitrogen and 3 hydrogens, apparently. Now we can't have differences in numbers of atoms of each substance, so we can put a coefficient out in front to make things, of a given substance, to make things balance. And here if we put a 2 in front of the NH3, that means we have 2 nitrogens at the end, balancing the 2 nitrogens to start. But of course it means we have 2 times 3 or 6 hydrogens at the end, which doesn't yet balance the 2 hydrogens we apparently start with until we put a coefficient of 3 in front, and 3 times 2 gives us 6. 2 nitrogens, 6 hydrogens to start, same numbers of nitrogens and hydrogens to end. That is a correctly balanced equation, and everybody is happy. Okay, next let's balance the reaction that takes place during photosynthesis. We have carbon dioxide reacting with water to form glucose, C6H12O6, and oxygen. And generally speaking, what we do is we balance element by element, kind of working our way one at a time from left to right, with a few suggestions for how to deal with certain situations. So first element is carbon. 6 carbons as a product means we have to have 6 carbons as a reactant. Next we balance hydrogen or oxygen, and in this case when we put a coefficient here it's going to affect both hydrogen and oxygen. We have 12 hydrogens at the end, so 6 times 2 would give us 12 hydrogens at the start, balancing the hydrogens. And now we note we're somewhat fortunate here in that if we put a coefficient in this spot in front of the oxygen in the products, the only thing that's going to be changed is the oxygen, and that's what we need to fix. So we're fortunate in this case that things just kind of fall into our laps in terms of ordering. And now you have to be a little careful to add things up right. 6 times 2 is 12 oxygens due to the carbon dioxide, and 6 times 1 is 6 oxygens due to the water. So that's a total of 18 oxygens on the left. That means we need 18 oxygens on the right, of which 6 oxygens are already in the glucose. So 18 minus 6 is 12, so we need 12 more oxygens, and what makes that work is 6 times 2 right there. Okay, the next reaction is the complete combustion of propane. Perhaps you have a propane grill. And propane is a fuel. It burns, it undergoes combustion. And combustion requires oxygen. And if it's a complete combustion of a carbon, hydrogen, and maybe oxygen containing fuel, then complete combustion of that type of fuel produces carbon dioxide, CO2, and water, H2O. So the unbalanced reaction equation for the complete combustion of propane is C3H8 plus O2 makes CO2 plus H2O. And to balance, we'll start with carbon, 3 carbons on the left, need to have 3 carbons on the right. Then we move on to the next element, and here we have hydrogen or oxygen we could potentially balance. And a general suggestion for balancing is if you ever have an element by itself, like oxygen, save that till the end. Like in the previous problem, if this element's by itself, a coefficient put here will only balance the oxygen, whereas a coefficient put here will affect both hydrogen and oxygen. So definitely do hydrogen next, 8 hydrogens to start, 4 times 2 gives us 8 hydrogens to end. And then we note we have 3 times 2, which is 6, plus 4 times 1, which is 4 more. So 6 plus 4 is 10 total oxygens in the products, which means we need 5 times 2, or 10 oxygens to start. And that's the correctly balanced equation for the complete combustion of propane. One more, let's do incomplete combustion of propane. And this happens if the oxygen supply is limited. For example, if you're grilling inside a closed garage, that's dangerous actually, because incomplete combustion still requires oxygen, but it produces carbon monoxide instead of carbon dioxide. And carbon monoxide is odorless. It binds with hemoglobin much more readily than carbon dioxide does, or for that matter than oxygen does. And this prevents oxygen from being carried effectively throughout your body. And so even small amounts of carbon monoxide can actually make you pass out or potentially die. So very dangerous situation potentially. What we're going to do is write the balanced equation. So C3H8 plus O2, same as for complete combustion, but it makes carbon monoxide CO and then water H2O. And we start balancing as before, 3 carbons, 3 carbons, still 8 hydrogens, still 8 hydrogens. But now the oxygen is going to be different, and we notice that 3 oxygens total from the carbon monoxide plus 4 oxygens total from the water gives us 7 oxygens at the end. That means we need to have 7 oxygens to start. So what times 2 gives us 7? And if you're tempted to say, well, nothing, no, there is something. 3.5 or 3.5 times 2 gives us 7. But this is objectionable from a chemical standpoint. Mathematically, it's okay. 3.5 times 2 is 7. But we can't have 3.5 oxygen molecules and still have them be oxygen molecules. So we have to have this ratio, 1 to 3.5 to 3 to 4, but we have to have all whole number coefficients. And so the solution to that, of course, is we just multiply everything by 2. 2 times 1 is 2. 2 times 3.5 is 7. 2 times 3 is 6. And 2 times 4 is 8. And now we have both mathematically a correct equation, but also chemically, where all of our molecules are whole molecules. And in general, with chemical equations, the correct balancing is the lowest but whole number ratio. So if you ever end up with a ratio of numbers you can all divide by 2, you simplify. And if you end up with fractions or decimals, then you multiply by the smallest number to make everything a whole number ratio. So you should do enough practice with writing and balancing chemical equations to be able to do this correctly and quickly. And you should also know what the products of complete and incomplete combustion are, and of course what is needed for combustion in general. And that's it for the Introductory Chemical Reaction Equations screencast.